what I'm going to cover very quickly, I always do a background because I don't. This might be a good reference later. A little bit about the configuration abstraction that we do and why, and some of the tools. A little bit of background on that, and then I have cooked up a bit of an example that actually came out of a conversation Trevor and I had. I don't know, what was it, 6-7 months ago now, where he wanted to chop up a defconfig and try to figure out what parts he needed and how to sort of stitch some of the fragments in. And I said, you know, I've had requests for that for a while. So I sat down and finally wrote a tool that would help with that. And we went back and forth. And I said, you know what, I should basically do a talk about this tool and use it to highlight, you know, what you can do by hand and what we can now do, maybe get a little assist from this tool. And that's how we have landed here. So as I mentioned, what I want to do is just highlight and repeat, and anybody who knows me, I don't know, complain and repeat and berate and about the configuration and BSP challenges. And it's not about what kernel source or specific kernel tree you choose. You can kind of do what you want there. I won't judge you too much. And then I want to introduce the configuration data and tools, and then show a simple creation and extension of some of a BSP. So I always have to pitch a little bit of linux-yocto, and this is what this stuff is mainly tested and based on. It does work. You'll see in my example, it's not against linux-yocto in all of them. Just that we use linux-yocto and OE core to drive sort of some of the tightly coupled kernel packages and make sure they work for everybody's kernel tree. You know, libc headers, perf, lttng, systemtap, you'll see my name on those commits. And, you know, recently fighting through the v5.16 DT schema validation changes, you know, things like that. We use it to drive, to make sure that the general support works for everybody's kernel packages and kernel trees, but we also then use it for, we carry some SOC patches in there if we want to make them more available, and we use it to drive some of these stacks that, for example, meta virtualization, some of the other layers need. And I will point out that, you know, that is many of the branches, it's identical. There are no changes merged to some of the branches in linux-yocto on purpose, so we can build stable and different things bit for bit the same. And the other thing that gets carried along with this is the kernel configuration and metadata and tooling, which I will say is maybe more important than you think when you have a single board and a single configuration and a single image that you're supporting. It doesn't seem important, but as soon as you try to scale that matrix, it does become more important. So this talk, as I said, I'm going to focus on kernel configuration and management, not about the tools, not about linux-yocto, not about the branching. But the tools that we'll be using here, I did a talk last summit on it in a little bit more detail. You know, it's all about scaling through the configuration and the management of, you know, 6+ kernel versions. There are actually more now because we're supporting some of the older LTS branches for longer, 6 architectures, 14 boards, right? And with bunches of different features. So what I'm talking about is we're talking about the very tiny, maybe visible part on the end of what we do with the tools. But they're built to, you know, manage this sort of level of complexity. And it's like, no, we can't equally maintain it with directories full of patches, because these were created due to working at an OSV, trying to maintain defconfigs and directories full of patches, and nearly burning ourselves out doing that. So a quick overview of what we do, or what the tools do with kernel configuration. So the end goal is to abstract the details from the integrator. We don't want to reference specific kernel config options unless we can help it in the sort of recipe or anonymous Python or whatever have you. We don't want to reference specific configuration options, because that is kernel version specific, and a lot of them do change. You can go look at the history in the kernel cache, and you can see every kernel version as we throw out obsolete options, as we bring in new ones, as we change tri-states, and they do churn over time. So you'll run into a lot of difficulties if you start sprinkling board specific and kernel version specific knowledge throughout your system. We want them to be able to support dynamic feature addition and removal. So, you know, if you are doing add-on boards with sub boards and things that get pulled in through containers, you know, we kind of want to be able to support things like that, not necessarily at runtime, but definitely at build time. Trying to avoid just in case configurations. So we try to keep some of the base configs smaller and not configured in case somebody wants to run systemd or sysv init, or they want it as small as possible, or they want to run Docker later, or they need C groups, or they need C groups v2, or you can turn on everything and that's fine, but that's not really what what we want to do if we do care about some of the metrics of, you know, performance and maintainability and boot time and different things like that. And the other thing that they have always done, it's sort of badly named, and I try to use the term split the policy from hardware configuration. In the same way, a lot of people say they don't want the evil vendor BSP to tell them what kernel tree to use. I don't want the evil vendor BSP to tell me what type of C groups I need on, what kind of net filter options. You know, I don't really care about their that part of their configuration. I want to know what hardware options are required to boot the board. So the tools tried to split what I call policy from hardware configuration. And they're literally called, not surprisingly, non-hardware and hardware in the implementation of the actual configuration fragments. And we run different audits based on the type, because if you mess up a hardware configuration, you might have a boot failure. If you have a policy change that's different, well, it might just mean something later on doesn't work and it's not quite as critical. The fragments, as you say, as I'm saying, they're split into this kernel metadata, kernel cache, if you will. It was named because it backed the kernel, so it was a hot sort of layer for configuring kernels. It's built with these fragments. You know, it's fine. You can use them in your layer or kernel BB appends or you know, things like that. And that's perfectly fine. I do it in meta virtualization in a bunch of places, but even better is if they can be collected and reused in sort of a more centralized location, so you don't have to hunt up everybody's layer to see how they configured Docker, for example. They do have some integration with the build through the kernel features variable, and that allows some mapping of distro and image features to abstracted kernel requirements. So the names of the kernel features are not the names of the options on purpose. You can say, I want, you know, USB, and we then, based on the kernel version you're building, it will eventually find out what you need and we'll configure it into the build. And I say they're useful for machine features if you're careful, because a lot of the times we used to run into people saying, well, I turned on, I don't know, config a bus and it didn't do anything. It's because your hardware doesn't have the bus. So you can turn on those config options all you want. It doesn't mean anything in that point of view. So if you're careful, you can map sort of the hardware features to machine features and have a little bit of dynamic configuration there as well. The kernel cache that I just hinted about, like I say, the name's a bit old now and sort of not exactly what it does, but the kernel cache fragment collection, it can be used without linux-yocto. Obviously, it can be used with it. It can be used without adding the repository to the source URI. And I have a link to something that I did in meta virtualization that I'm testing out, because meta virtualization in particular tries to turn on some kernel features through BB appends. And if you don't have the right fragment layout, people were getting errors. So we came up with a way to actually separately clone and make the kernel configuration fragment repository separate without you needing to add it into your kernel's Git, into your source URI of your kernel recipe. So it's sort of completely arm's length at that point. And of course, you can override what is in that centralized baseline kernel configuration. You can override it through your layers or normal semantics of overrides and configuration. All right, I should do a time check. 11:56 here. All right, I better speed up. Here's a sort of reference BSP configuration. People will hear me say, I don't want your defconfig, and I probably don't. But they are a great resource because they are the way that it's easiest to say, for somebody to say, this is the full set of features that I tested the board with, right? So they're a great starting point, or a finishing point, as I said, depending on your requirements. It might be all you need if you're only doing a single board and you want to run a vendor exact configuration, and then you're done at that point, and there's absolutely nothing sort of wrong with that. And they're off, but the biggest problem is, and I've seen the commits and the churn where there's often they're demo configs more than def configs, where they say, well, we want somebody to run Kubernetes or Docker or some of the new NetFilter or BPF or this or that. So a lot of things get turned on in these configurations just in case somebody might use them, and that's sort of a problem. And so depending on your requirements and the amount of churn that you have, they may or may not be appropriate. All of our kernel and linux-yocto reference BSPs, they're using the configuration fragments, which is a set of BSP options that are just about the hardware plus a base kernel type plus features that get added through the metadata of the recipes that I was mentioning. All right, so we got about 15 minutes by my count to go through this new tool that I wrote.
You've got 15 minutes, but the next talk doesn't start until 30 after, so we could always, there's a bit of a break after. Yeah,
I'll move along fairly quickly anyway, and maybe we'll, so say you want to create or extend a BSP, right? There's a million and one ways you could probably do it. There's a lot of options, but generally, you choose the kernel tree. As we all know, that's not always a choice you can make. You're handed some 4.19 recipe based off of somebody's fork of something, and that's, you don't really have a lot of options unless you want to export the patches and uprub them yourselves. So you know what kernel tree you're building against. You select the configuration, which is probably a defconfig. You build, boot, and test, and then you modify the configuration, right? And so, did it boot too slow? Were you missing a NetFilter option? Did something, it used to be even worse for this, but there's some small feature that was wrong for latency or RCU, or something was wrong, or the right different type of memory management. So, you tweak it, and then of course you repeat those until you're happy. We're never happy, but until you're satisfied, I guess, until it's good enough. And then you finalize the configuration and your machine definition, and then you ship it, and you never update it again. You leave it on Sumo for the next 13 years. And have where's my Lego figure? So that's sort of, a really high level view of what you might do when creating or extending a BSP. So if you wanted to do that with the Yocto kernel tools, plus linux-yocto, I always have to plug linux-yocto. If you're extending an existing linux-yocto BSP, you could just add your own configuration fragment through the source URI or through kernel features. So you could just specify that you wanted to add something on top, the base BSP, the base kernel type, the features, and the BSP get applied, and then your stuff gets applied on top. So you get a chance to turn things on or off or change things. So that's pretty simple, and it's not so interesting for this presentation. So that's the only all I'll mention on that. But I will plug in the thing I mentioned with that Trevor and I did. The common question we get is, hey, I tried to turn off option foo, and it didn't turn off when they do this first case. And well, if something in the kernel tree selects or otherwise depends on an option, you can't turn it off. And there are audit tools that can help you built into linux-yocto flow that can tell you about that, and that's a whole different talk, and I've done it before, and I won't go into it. But yeah, so within bounds, this first approach is simple and it works. So if you're doing it, say maybe from a reference defconfig, so you do your build and your boot test, you add feature fragments, and then you might want to split out the hardware from the policy options because you want to define your own configuration features for your software yourself. You don't want to take them from the defconfig. So that is another way to go about creating a sort of split up configuration for your for extending a BSP. And that's the one I'm going to talk about for the next few minutes. So I have here, consider the following stable recipe where this is building qemu ARM 64. It's using, this is v5.14 base, which is exactly Greg KH's 5.14 stable. In this case, it's pulling it from linux-yocto, and it's doing a few things. So it's pretty small. This is it. This is the whole, this is me building the kbuild defconfig from in the tree. It's not using any of the linux-yocto fragments. So you can, with this BSP, you can build, I called it Linux stable. You can bit bake it, and then you can boot qemu ARM 64, and you can see, yep, fantastic. I came up and I booted. But that's about all you know. You built a defconfig in it and it ran. So what if though, if you wanted to, again, like I said, you didn't want to fight with the defconfig, or you didn't want to track the defconfig, or you wanted to freeze some configuration, and you don't want to start from that in-tree defconfig and only add to it and fight with the selects and delete. So if you don't want to do that, you might want to be able to split the defconfig and pull out the hardware options and just set the software options yourself. So in talking to Trevor, I finished writing a tool that I'd thought about for a while, and it's in the Yocto kern tools repository. It's called kget-config, and it leverages the existing set of kernel configuration metadata that we have, or it can actually do some analysis on the tree, which is, again, some of that legwork that is done way in the background that nobody sees. I pulled in some of the tools that I use to update options between kernel versions, and it does some classification on the options. So some rough automated classification, so you can actually do it without using the existing metadata. So, what it can do is it can split the fragments or defconfigs into hardware and policy. It can create a skeleton BSP definition. It can generate a report about available policy fragments if you want to turn something on. It can query the kernel cache for fragments and options, but what it can't do is perfectly create a working BSP every time. And I think I even have my example of why I put that last can't in there, because when I ran my tests, it didn't create a working BSP. So these are the two types. I'll talk about them in detail when I go through the specific slides. So this is me running type 1, where I'm actually using the this is where I'm using the kernel source, and I'm not using the existing linux-yocto kernel metadata. So I ran this, I pointed it at the defconfig I wanted to process. I pointed it at the kernel source that I was using, which could be whatever tree you want. And what it ended up putting out is a BSP, my BSP hardware, my BSP policy, and some fragments. And it even made a K-types base that's automatically included by the BSP, but that's empty right now, because that's just might be somewhere that you want to start storing your own non-BSP specific policy. So it kind of roughs out that framework for you. So you can see, if I look at what that main my BSP configuration entry point was, all it did was include this base kernel type. It sets the hardware options to be your my BSP's hardware configuration, and it automatically comments out the my BSP policy.cfg, which is the non-hardware options that were found in the defconfig. And this is where the asterisk is in, because without the linux-yocto metadata, one option got turned off that you need. config Unix got turned off when I ran it. And so when you boot the new split BSP with systemd enabled, it traps because it doesn't have Unix sockets. But that's so you can just, if you would just go take away that commented line and reboot, it would actually work because it is actually the same. It's just split. So if you look at it, it found, you know, in the defconfig, there's roughly 1,215 options. If you look at the what the tools automatically found were BSP hardware options, there was 1,078 of the 1,215, and 137 of them were not hardware. And this is all using the automated tools that know some classifications inside of a kernel tree and what directories tend to do it. So this is what was used to create that split. So you've done that split. And then all you actually have to do is copy the generated kernel cache or just point the output directory at your layer, if that's your thing. You copy it into your local layer. You would drop the kbuild defconfig line from the recipe, and you would just map the kernel machine to be my BSP now. And that's it. So you, and you would add this new generated kernel cache directory to the source URI, and then map it to tell it to look for my BSP in there. And the tools automatically will go find that framework that I just highlighted. It will build, and it won't boot because I was using systemd and config Unix gets turned off. So that's what that asterisk means. So you then have to then go figure out why it didn't boot, which luckily wasn't too hard to do. The second way to do it, and I just wanted to show this, is if you use the kernel cache, the existing classification and options. And the only difference there is we've gone through some of the big directory subtrees in the kernel, and even though most things say in drivers are hardware options and we want to leave them as hardware options, there's some that aren't. And so we've done some finer grained classification. So if you remember, that type 1 had 1,078 hardware options. When I ran that same command referencing the linux-yocto kernel configuration metadata, it has 1,054. So we found a few more options that were not that were considered software, and yanked them out of the hardware thing. So if you do a diff, in this case, I diffed the hardware fragment from run 1 to run 2, and some things came out like config dev temp fs. Yeah, that's not a hardware option. It pulled that out. Block dev loop. Again, I'm not saying they're not useful options, but ton, veth, virtio, net, these are not hardware options, right? So these are something that, depending on what I'm running on the BSP, I may or may not want to configure myself. So we got a slightly more fine-grained sorting of the options when using the reference data. And another thing that the tool can do that I mentioned is useful if you are hunting around. So you're doing the split and you don't necessarily want to write a BSP definition. You just want to sort of generate, if you just generate it on the fly without writing your own, it will actually go through and it dumps out an audit of what it found were hardware options. And this, I kept a few of them in the top portion there, which they're obviously, they actually are hardware options. But it then will go through and say, well, these are what looks like policy options in the def config. And it says, POSIX MQ, audit, no Hertz idle. And it looks, if you run it with the reference features that we have for configuration fragments, it will go through and say, hey, if you want to turn config audit on, you would have had that if you used the base K type. Or if you want to turn on, what's another one here? If you want to turn on, no, I don't have any good ones. SysIV, they're base, but and if there's something that's not mentioned, there is no feature fragment for it, it tells you there is no fragment that references that option. So it might be something that you want to turn on. I guess there's two good ones at the bottom. If you want mem control group or swap, then you could get those from our C groups fragment. So it tells you that you could then go to your BSP skeleton and you could just include those features and they'll get turned on your build. So it tries to give you hints on where you could find some of these policy options in the metadata. And the final thing I made it do while working through writing that audit of the existing options and what you could and couldn't add, I wrote a little bit of a tool that is a light wrapper around just grepping through the kernel cache, which is of course what I do most of the time. And so, you know, say you wanted to find out what provides config debugfs, then you could query the kernel cache on your disk, and it would tell you that, you know, 7 config files do reference it. So, you know, we have a fragment config debugfs.cfg, and it's included by this feature and different config files that are turning on. So you can find out sort of right down to some of the BSPs are turning this on directly when they probably shouldn't. But yeah, so there's a way that you can, it saves a little bit of grepping, and it might be easier for the new user to figure out what fragments provide what and where they're included from and how they're used. And if it turns out to be useful, I could add all kinds of things that would draw dependency trees and different things between the options. So future work, there's always more work. I'm continuing to try to make the automatic splitting heuristics a little bit smarter to bring them closer to what you get when you run it against the existing kernel metadata repository. Allow us to know how to classify a few features and maybe feature blocks like networking, for example. Like say that, hey, you really probably don't want to turn off config net, whether it's a good idea or not. You know, let the tool actually, some of that audit where I'm telling you options exist, or if you want a high level feature, then allow it to let you create a feature fragment and start writing them into your own collection of fragments automatically. So, you know, you could ask for a high level feature, like I said, config foo, and it has a config networking dependency, and there's all the tools for in linux-yocto that do the audit could figure out exactly what you need, and you could write your own configuration fragments. So that's something that we could also do. And of course, I'm working on consolidating some of the more, you know, we have a Docker, unfortunately, a Docker configuration fragment in meta virtualization and another one in the main repository. So now that I can split out the need to add the kernel cache to your source URI and a kernel recipe, I can maybe do some more consolidation of options in a single place so they don't get out of sync and cause subtle runtime errors when they do differ. And that's it.